Have you ever stood on the side of the road as a car raced by, hearing its high-pitched approach drop to a suddenly low-pitched frequency as it moved past you? This occurs due to a wave phenomenon in physics called the Doppler effect, which is the change in the observed frequency of a wave that occurs when there's a relative motion between the source of a wave and its observer. The Doppler effect can thus be perceived in different ways, depending on relative motion. Let's go back to the previous example of the car to explain this. Imagine a car moving towards you, a stationary observer, and is emitting sound, such as a siren. This sound can be represented by circular wavefronts. As the car moves towards you, the wavefronts of sound between you and the car are crowding together. These wavefronts of sound thus meet you more frequently and represent a shorter wavelength than what is originally emitted by the car without the effects of crowding. Such is the case for if the car is stationary and the sirens are going off, then there will be less crowding and it will be less loud while you're positioned in front of it. This means the frequency of the sound becomes higher to you. So what you observe is a higher pitch, which is determined by frequency. Conversely, once the car has moved past you, the wavefronts arrive at your position less frequently, making the measured wavelengths larger than at the source due to the wavefronts being further apart. That means that the pitch becomes much lower than both the original pitch emitted at the source and the pitch at which the car approached you. This is the Doppler effect as it applies to sound. However, it also occurs with light waves. Have you ever heard about the convincing evidence that we live in an expanding universe? We know this because of the Doppler effect of light. If a source of light moves away from us, considered a stationary observer, the frequency decreases and the wavelength increases, exactly like the example with the car and the sirens. When this happens with a source of light, we call it a red shift, because longer wavelengths are associated with the red end of the visible light spectrum. Contrastingly, if a source of light is approaching us, we observe a decreased wavelength and observe a blue shift, as shorter wavelengths come from the blue end of the visible light spectrum. So, we know that the universe is expanding because light from distant galaxies measured on Earth show a redshift, meaning galaxies are moving away from us. According to National Geographic, there are also plenty of evidence that the universe is expanding at an accelerating rate. Given that we are not all astronomers, it is simpler to talk about some of the more common uses of the Doppler effect in our everyday life. A great example is when the police use a radar gun to check for speeding vehicles. The radar gun sends out radar waves at a known frequency, which then bounce off the desired vehicle and reflects back towards the radar gun at a different frequency depending on the direction and speed of the vehicle. Then finally, the radar gun computes the speed by measuring the difference between the emitted frequency and the reflected frequency. The faster the car is going, the more the frequency will change.